Hello and welcome to Module 4. In this module we will be covering Chapter 27, the Theory of Relativity, and this module is going to go for 2 weeks because of the length of the chapter. Let me just show you the course schedule here. You can access, by the way, I've been getting email from students, and from the type of question they're asking, they are not really looking up any of those items that I am posting here, and especially the course schedule. A lot of you are asking, not a lot of you, some of you are asking when is the midterm exam, and it is shown clearly in the course schedule. You can access the course schedule in module 0 in the course. You see that right there? And if you click on it, you'll get to this page right here. You can actually download the Word document. Just click on this file right here, and you can download it and keep it for your own records. And then the course schedule is divided into modules and the dates of each module and so on. So we are right now in module 4, and we're covering relativity, and it's a 2-week module. So we're going to do relativity chapter. And the due date on it is the 26th, so it's going to be for 2 weeks. And please remember, during the week of that 26th, there is a midterm exam number 2. So that's going to be starting on, I will open up the exam on the 24th of April, which is a Friday. Here, let me show you the calendar. Here's the calendar. The 24th of April is a Friday, so it's going to open up Friday morning, Saturday all the way until Sunday 11:59 right there. Okay, we are today in Easter Sunday right now, so it's going to open for those 3 days here, and then you'll take the midterm exam. The midterm exam is going to be over all the chapters that we have that we have covered since midterm 1, which basically chapter 23, chapter 24, chapter 26, and chapter 27. Okay, you got it, everyone? Okay. And then we have another 2-week module, which is the very last module, really. It's nuclear physics. It's going to go for 2 weeks. Maybe I'll give you 2 video lectures on this one here, and that will be the last one. We'll be then done with the semester. And then the final exam is, I need to look up the final exam schedule for this year, given that we have a transition to online. I'm not sure how that would work, but it's going to be during the final exam, regular final exam week. Okay, and that's it. And by the way, I mistyped the numbers here. So 1, 2, 3, 4, 5, 6, 8. So there should be 7 here. Module 7. Okay. Okay. All right. Let's go back to the chapter that we're going to cover, which is the special theory of relativity. There are 2 theories for the theory of relativity. One is called the special theory of relativity, and the other one is the general theory of relativity. The special theory of relativity was created by, at least historically, by Albert Einstein in 1905, and then 10 years after, 1915, supposedly he came up with the theory of general relativity, which includes gravity. It's something that we're not going to cover. We're only going to cover certain aspect of the special theory of relativity. Okay, the theory here is divided really into 2 big parts, and that's why I gave 2 modules for it. 2 weeks for it. The reason is the first part is what we call relativistic kinematics, the nature of space, time, and lengths, and so on. And the other part is the dynamical part, where we talk about momentum, work, energy, kinetic energy, rest energy, and so on. So there are the 2 parts. So I thought 2 weeks should be sufficient for you. Before I forget, I have changed the homework problems. I have noticed there are 2 students who already finished the homework for chapter 27. I guess they are studying ahead. For those of you, I hope you're listening. Make sure that you go back to your mastering, because I have changed the problems. I actually took out 3 problems that they were homework, but they were a little bit hard. Okay, they were difficult. The level of difficulty is a little bit hard, so I took them out and I replaced them with 2 that are a little bit easier. Okay, so basically I reduce the difficulty of the homework just a little bit because I'm not around you guys. You're not, I'm not in class, and you can't just ask me questions easily. So I kind of reduce the level of difficulty of the homework. So for those of you who have finished the homework already, please go back, and there are 2 more problems that you need to work on. And some of those problems that you already worked on, I believe 3 of them, I forgot which numbers. But anyway, just you need to adjust that, okay? That's all. For those of you who have not done the homework yet, this is no issue for you. You're just gonna, it's open, and you just start working on it. Okay, back to the chapter. I keep talking too much. So we're going to be covering the special theory of relativity, and we begin with what is called the postulates of relativity. Okay, and the postulate of relativity are 2 postulates. The first one is right here. I don't need to write it down. I'm just going to read it for you, and then I'll explain it. The postulate, or it's called principle of relativity. It says basically all the laws of physics are the same in all inertial frame of reference. Okay. Now, when we say the term inertial frame of reference, think of it like x, y, z. Okay, x, y, z coordinates. Okay, and imagine that x, y, z coordinates for example, let's say anything that is moving, say a car, a train, a spaceship, a plane, anything that you can ride, for example, and move through it, or even Earth, because we are riding the Earth and moving through space. So anything that you ride and then move, we can call it a inertial frame of reference. I'm trying to be as simple as possible with that. And provided that this inertial frame of reference is moving at constant speed. Okay, it cannot be accelerating. Okay, and I don't want to get into that. That's a little bit heavier physics. But basically, when you read the term inertial frame of reference, think of a coordinate x, y, z. The regular Cartesian coordinate x, y, or x, y, z, and it is moving, or maybe at rest. It could be at rest. Okay, or think of something like a car. I'm sitting in a car and I'm moving, or I am in a spaceship driving it, or or riding it, whatever. Okay, anything that's the inertial frame of reference. So basically, the first principle of relativity said all the laws of physics are valid in any inertial frame of reference. What that means, if I would do a lab experiment, let's say on Earth in a lab, okay, and I would come up with some result, okay, if I would do the same lab experiment on a train moving, again, not accelerating, I'll come up with the same result. Simple. In other words, if I go anywhere in the universe, whether I'm in a moving frame or a rest frame, and I do any lab experiment to come up with some law, or whatever, or create a model for something, I will come up with the same result, basically. Okay, you may think it's not a big deal of a law, but that's basically what it is. Okay, so all the laws of physics are valid in any frame of reference. That's basically what it is. Okay, the second one that is more useful for us should be here somewhere. There it is. It's called the invariance of the speed of light. Okay, let me read it for you. It says the speed of light in vacuum is the same in all inertial frame of reference. Again, inertial frame of reference like a spaceship, a car, or whatever, and is independent of the motion of the source. Okay, what does that mean? Let me explain it to you. Let's say, for example, I'm driving my car, going, say, on the highways, going, say, 40 miles an hour. Okay, you are, on the other hand, somewhere behind me, driving your car 60 miles an hour. I'm going 40. Let me represent it with maybe some diagram here. So let's say here is me. Oops. Black. All right, so here is me right here. I'm trying to draw a car. There we go. It's not a nice looking car, but let's say I'm driving with, say, 40 miles per hour, okay, on the ground, on the street. And you, on the other hand, here you are. You're going faster than me. Let's say you're going 60 miles an hour, okay? Of course, you're going to pass me, right? Eventually, you're going to pass me. Now, when you pass me, if I'm looking at you as you pass me, what is your speed relative to me? It's going to be 20, right? You agree with me on that? In other words, let's say that you and I are going 60, okay? Let's say I'm going 60, and you are also going 60. And let's say we are on the same, you are in the opposite lane right beside me. Well, we could actually talk to each other, right? You're not passing me, I'm not passing you, because we're going the same speed. So I can say that your speed relative to me is really 0. You're not going anywhere, even though we're going 60, because I'm going 60 the same as you are. Now, if I go 70, I'm going to pass you by 10. Make sense? So here we say that speed is relative. Relative, okay? Speed is relative, okay? Now, the second postulate says, this is fine, but when it comes to the speed of light, see, it's actually, you can't do that. In other words, let's say I'm in a spaceship going with a speed c, okay? And someone else going, with a speed, let's say, how do I say this? Let's say somebody going in the opposite direction with a speed c. Let me go back to this. Let's assume you're going 60 miles an hour here, okay? Let's say someone else is going in the opposite direction. Here it is. Let's say you're going 60, right? Let's say he's going 50. So as he passes you on the other lane, what's his speed relative to you? It would be, you add up the speed, it will be 110. You agree with me on that? He's going to pass really, really fast. You see what I'm saying? So, but this kind of relative speed does not apply to high speed, to the speed of light. If I'm going c, a spaceship going in the opposite direction, I'm not going to measure 2c. I'm going to measure c. Okay. In other words, no matter what, the relative speed when it comes to the speed of light doesn't work. Okay. That's basically what it is. Here, the speed of light in vacuum is the same in all inertial frame of reference. Whether this car going in this direction or that car, whatever, and is independent of the motion of the source. Okay. That's the meaning of it. All right. I'm just going to be, there are a lot of parts here that we're going to skip. Now, the nature of simultaneity, you can read it, but there is no homework problem that are related to it. It's more of a philosophical thing. So I'm not gonna talk about it. I'm trying to reduce the amount of coverage in this video because I can't talk for 2-3 hours. I mean, my limit is 1 hour. Then I will get very, very tired. Okay. Now we talk about relativity of time. Okay. So we have something called the time dilation. This is an important concept. Again, we are in the first part of relativity, which is the relativistic kinematics. Okay. We have time dilation. Time dilation says the following, is that when it comes to time, when somebody, let's say somebody on a spaceship, let's say you have somebody, here's a spaceship, okay? So this is a spaceship, and it's going at relativistic speed. Now, when I say relativistic speed, I'm talking about a speed that is greater than 10% the speed of light. Okay, roughly. The 10% is not a magic number or anything, but roughly. Okay, so when you're talking about, if it's 10, remember the speed of light is 3 times 10 to the 8 meter per second. So 10% the speed of light, we can calculate that. But that's basically, if the speed is large, so we would call it relativistic speed. In other words, in this case, the laws of classical Newtonian mechanics, which is all the laws that you have studied in 151, and big part of it in 152, don't work anymore, or will produce large error. Okay, so you need to revise those laws into what we call relativistic laws. Okay, if the speed exceeds, again, roughly 10% the speed of light. Okay, so here in this chapter, whenever we talk about speed, we are really assuming it is larger than 10% the speed. As a matter of fact, most of the time is greater than 80% the speed of light. Something like 0.8c. When we say 0.8c, it means 80% the speed of light. 0.9c, 90%. 0.99c, 99% the speed of light, and so on. Okay. All right. So let's say there's a spaceship, and let's say you are in this spaceship. You are, okay, and you have a clock, you have a watch in your hand, okay, and you're going at some relativistic speed, whatever speed you want. Let's say 0.8c, okay, and you look at your clock, and it's ticking normally, okay. It's ticking, you know, just like as if you're on the ground. You don't even feel any difference, okay. You tick, 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 and so on. However, for somebody, let's say on Earth, let's say this is Earth, and here is an observer here on Earth looking at you, and somehow he is looking at your clock, okay? He's measuring your clock, okay? So this is an observer on Earth. What he will see is that the ticking of your clock, which ticks every 1 second, tick, 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 he will see that the ticking is really slow. In other words, between one tick and the other is like tick, tick, tick. In other words, every 2-3 seconds, the tick becomes. In other words, what happens, he will observe that time slows down. So time slows down for you, you know, for you on the spaceship. Okay? This phenomenon is called time dilation. Okay? Now, the time that is measured by the guy on the observer, excuse me, the person inside the spaceship, that time, we call it the proper time. So, proper time, time measured by observer in the spaceship. Okay? That's the proper time. Relativistic time, which is the time measured by this observer here, time measured by observer. Oh, when I say big O, it means observer. Observer outside spaceship, for example, or outside the inertial frame of reference. You got it? Okay. And so how do we compare the two? You know, this is the time, this is relativistic time, let's call it delta t. And this proper time, let's call it delta tp. Okay? Well, how are they related? In other words, is there a way that I can measure it accurately? And the answer is yes. It's a time dilation equation, and it's equal to delta t, which is the relativistic time, is equal to gamma delta tp. That's the formula. Write it down, because we're going to be using it, okay? So Tp here, the proper time, and what is gamma? Gamma is called the gamma factor. It pops up in just about every single relativistic equation, is equal to 1 over square root of 1 minus v squared over c squared, okay? Again, you need to remember that. That's the gamma factor. The gamma factor. Okay? Well, let me give you an example. Let's say, for example, I'll give you a couple of examples at least. Let's say let's make it, let's give some names. Let's say John on spaceship measures a time interval of, let's say, pick a number, say 5 seconds. You know, let's say, he's doing some experiment, and then for the outcome to come out, it took 5 seconds for whatever process he's doing. Okay. Now let's say Kathy on Earth. Okay. So what is, let's say the time spaceship measures the time interval. What is the time interval measured by Kathy, who is on the ground, who is on Earth? I kind of said that already. Anyway. Okay, so Kathy, according to Kathy, Okay, maybe I should say this, according to Kathy. What is the time interval measured by Kathy, who is on Earth? Now, first of all, we need to decide what is the proper time here. Well, the proper time is John, because he is measuring that in his own frame. That's the meaning of the proper time, is what you measure in your own frame. Okay, so proper time, I'll write it down. Proper time, time measured in your own frame. I read that already. I said spaceship, the same thing. In your own frame. Okay, so here the proper time, TP or delta TP, is 5 seconds. Now I want to know, oh, we forgot to mention that, let's say, the speed of the spaceship here, I'm sorry, I'm making up this for this problem as I go along. Speed, let's pick any number, let's say 0.8c. All right? Okay. So I need to know what is the relativistic time as measured by Kathy. Okay? So how do we do it? Well, it says T measured by Kathy is equal to gamma TP. First thing you do, find gamma. Gamma is what? 1 over square root of 1 minus v squared over c squared. Let's plug it in. So that's going to be 1 over square root of 1 minus 0.8 c squared, right, over c squared. You follow me so far? Well, that will be 1 over. It's kind of tedious to do, so get your calculator out, please. We are ready to calculate that. 1 minus. Of course, the c squared and c squared will cancel out. Do you agree with me on that? You're left with 0.8 quantity squared. And I'm going to use my calculator. One minus 0.8 squared. Here's my calculator. 0.8 squared. 0.64. I should have known that. That was dumb. 0.64. And then you're going to calculate. You're going to take that. 1 minus the answer, and then you take the square root of that, square root of the answer, and then the reciprocal of the answer. Answer, anybody got the answer? 1.67? Is that true? 1.67? Let me do it again one more time. I thought it would be larger than that. So we have here 0.864. Then you take the square root of that, and then the reciprocal. 1.67, that's true. Okay, so it's 1.67, okay? So now, here's the gamma factor. There is no unit, by the way, for the gamma factor. It's just a ratio, not a ratio, I'm sorry. It's just a fudge factor, okay? Now I go back here. So what is the time measured by Kathy? So gamma is 1.67. Multiply this by the proper time, which is 5. So I take that and multiply that by 5, and the answer is 8.33. So Kathy is going to say that it took the time, or the time interval, it's not 5 seconds. For her, it's slower. It took 8.33 seconds. You got that? That's basically how you calculate the proper time, the relativistic time. All right, let me give you another example. This one is a little bit more realistic. Okay. We have another example. I think this example in your book, I'm not sure where, but it's a famous example. There is a particle. It's called the muon. Okay, and this muon is a particle. It's about 200 times the mass of the electron, and those particles are formed in the upper atmosphere, and they come towards Earth, and they are formed, and then they come towards Earth. They penetrate the atmosphere. They go through all the way to the surface of the Earth. Actually, as a matter of fact, as you are sitting here watching this video, you are being bombarded by billions and billions of muon. You don't feel it; they're very, very tiny, but they are there. Okay. Here is the funny thing about them: the muon, when they are created at the upper atmosphere, they live. So their lifespan. I'm going to call it T, is 2.2 microsecond, and then they die. They kind of fizzle out. They convert into energy. They convert into something else. Okay, so they live for this time. Now, this time span in the muon's frame. In other words, if you are riding the muon and with a watch, you're going to say this muon lived for a time of 2.2 microsecond. Micro is a millionth of a second, okay? Span. Now, here is the upper atmosphere right here. Here is the Earth right there. That's the surface of the Earth. And the upper atmosphere, so they are formed here, and then they shoot toward the Earth like that. And they live for this time period in muon's rest frame, and they go at a speed toward the Earth at a speed of 0.99 c, 99% the speed of light. Okay? All right. Now, we know that from the upper atmosphere to the surface of the Earth is roughly 4,000 meters, which is roughly 4 kilometers. Okay? The question is, how do they manage to get here to the surface of the Earth? How do they manage to do that? Let me show you what I'm saying. See, if I know that their speed is that, and I know their lifespan, 2.2 microsecond, well, the distance they're going to travel, x equals to, the maximum distance is vt. So their velocity is 0.99 c, which c is 3 times 10 to the 8, multiplied by 2.2 microsecond, which is -6 seconds. So if I calculate that, let me calculate that. You go ahead and calculate with me, please. So we have 0.99 times 3e8 times 2.2 e minus 6. Answer, they're going to travel a distance, the maximum, before they die, 653.4 meters. Do you see the problem? If they're going to if they're going to travel only this much, which is not even 1 kilometer, how do they make it to the surface of the Earth? Even though, because the distance from here to here is 4,000. How do they make it? If they're going to die somewhere right here, they're going to die. And that's it. They're going to die. But we still see them here at the surface of the Earth. Do you see what I'm saying? Well, if we don't understand relativity, we don't have an answer to that. It's a mystery. But let's use relativity and see why the muon actually make it to the surface of the Earth. As a matter of fact, like I said, you are being bombarded by them right now. And we're going to use time dilation. Well, here is how it works. Remember we said that this time right here is in the muon's frame, which makes it what? This is the proper time, right? So the proper time is 2.2 microsecond. All right. So now what I want to know, remember we are on Earth observing them. So that means we need to measure the time, the lifetime of the muon from our reference frame. You got that? So to do that, well, from our reference frame is going to be gamma t sub p. So let's get that. Well, let me first get gamma. Gamma is what? 1 over 1 minus v squared. Well, the speed of the muon is 0.99 c, so that's just going to be 0.99 squared. The c's will cancel out, right? We've already done that. And then under the root, when you do this calculation for this, you'll end up with, I have already done that, it's equal to 7.1. So the gamma factor is 7.1. So now, when I take this one and calculate the relativistic time, this one here, as measured by an observer right here on Earth, And that's just going to be gamma t sub p, so that's 7.1 multiplied by 2.2 times 10 to the negative 6 second, the lifetime of the muon. And when I calculate that, it's going to be 15.2 microsecond. So that's the relativistic time. Now let me calculate the distance traveled by the muon, just like I did here. Right there, see that right here? I want to do the same thing, but now not for a, remember this t right here is proper. You see what I'm saying? But this is actually wrong calculation because we don't understand time dilation. So we have to take into consideration the time dilation factor. Okay? So in this case, it's going to be Vt relativistic, not proper. So the velocity is 0.99 times 10, 0.99 c, which is times 3 times 10 to the 8, right? Times the relativistic time, which is right here. That's 15.2 times 10 to the negative 6. Calculate that, and guess what? You're going to get 4,573 meters, which is within the range. Look at that. We said that they were roughly 4,000 meters away. Well, they travel even 500 more. And so they reach the Earth. And now we have an explanation why they reach the Earth. Well, because they are moving at relativistic speeds here, right? This is a relativistic speed. So we cannot ignore the fact that time is delayed. So we have to use the time dilation formula. You got it? Okay. Good. Another phenomenon for that is what is called the Linx contraction. Let me explain it to you. So we have time dilation and Linx contraction. Here's how it works. Linx contraction. If I have, let's say, a rod, here it is. Let's say of length L, and I have the rod sitting on the table, for example. Okay, of length L. Now, I'm going to take this rod and have it move at relativistic speed. You know, say 0.8 c, 0.5 c, whatever. Okay, so now the rod is moving at, here's the rod, and let's say it's moving with, some relativistic speed, say 0.8 c or something. Okay, what's going to happen to the rod? It will actually shorten. So it's no longer L. Okay, now it is something else. It's no longer L. It is something else. L, relativistic length. Okay, so in the frame of the rod, let's say you are right here, and you measure the length of the rod. That means this is the proper length. So LP is proper length. Remember, the proper means as measured by somebody on the frame. Got it? Now, when the rod is moving with some velocity, now what will happen is that this length will shorten. Okay? And it's measured by, if I want to get that, length is basically the proper length, L sub P, over gamma. We're not going to derive this stuff. I'm just going to show you the formula. There it is. Remember gamma? Gamma is, by the way, maybe I didn't mention it. Gamma is always greater than or equal to 1. Always. It's never below 1. Okay? So this will make it short. So this is short or smaller than. So in other words, L is smaller than LP, or LP is greater than L. LP is greater than L, and so on. Okay? Let me give an example. Suppose I have a rod, length, pick whatever length you want, let's say 1 meter, okay? Moving 1 meter in the frame, let's say in the frame of the rod, which makes it proper, right? Moves with, pick a number, say 0.8 c. So now the question is, what is the relativistic length? Or what is the length as measured by someone on Earth. Let's say it moves. Here's a picture. Here is the Earth right here. Here's the rod moving with very high velocity, 0.8 c. Okay? So what is this, the new length here? As, of course, the guy here he is, looking at it, with his meter stick, or meter stick, or whatever he wants to measure the length of the rod. This is LP as measured by somebody here, right here, right? Now, as measured by this guy, what is that length of the rod as measured by him? Okay, so we say that L is equal to LP over gamma. Okay, so LP is given to us. LP is just 1 meter. So this is basically a meter stick. So let me find gamma first. Well, gamma is 1 over square root of 1 minus V squared over C squared. So that's going to be 1 over square root of 1 minus 0.8 squared. You agree with me on that? And then we calculate that, and I think I did this one already for 1.8, 1.67. Remember that? So gamma value is equal to 1.67. Okay, so I go back and plug it in here. So therefore, the length as measured by this dude right here is equal to 1 meter divided by gamma, which is 1.67. And if I take the reciprocal of that, so 1 divided by 1.67 equals to 0.59, roughly 0.6. So as measured by him, he said, nope, it's not 1 meter, it's actually 0.6. See, it's so this phenomenon is called the Linx contraction. Did I write it down? Yeah, it's right here. Linx contraction, because the length of the rod shortens as you go faster and faster. Got it? Okay. There is example 1 is about the muon in your book, example 27.1. So I'm not going to do it. It's a little bit different, but it's kind of the same. There's no difference between them. So let me now move to the second part of relativity. Remember, I'm just covering what you need to know, okay? And by the way, section, I forgot what the name of the section. Let me go back to the book. Lorentz Transformation. We're not covering that, so don't waste your time with it. It is a big portion of the chapter, but I'm not going to cover it. Let me, Lorentz Transformation. Oh, I have the ebook, sorry. Well, let me see it since I'm here. Section 27.5, Lorentz Transformation. We're not going to do that, okay? Let me show it to you in the ebook. Oh, I have that. 27.5. Lorentz Transformation. This stuff, I don't think you need them. I mean, if I was, when I teach engineering physics, I would cover it because it's important for engineers and physicists, but for you guys, you definitely don't need it, okay? So we're not covering 27.5, you got it? So now we go to work and energy and momentum. I want to cover the whole thing today. I'll try to cover them. Okay. Now we come to the momentum. So far, let's just recap. So we said that. So we have time dilation, which means time becomes slow down. So time slows down as one goes faster, right? As measured by an observer. And then you have Linx contraction, which means length shortens as one goes faster. And then you have what is called mass increase. Okay? In other words, if let's say, so again, it is mass increases as one goes faster. What that means, let's say I am, let's say I am 80 kilogram. Say my mass is 80 kilogram. as I go faster and faster, my mass becomes heavier and heavier, more and more, okay? Now, at the speed of light, I would have infinite mass. But basically, that's what it is. So, mass increases, m equals m naught over 1 minus v squared over c squared. In other words, it is gamma m naught being the mass at rest. So, m naught is mass at rest, or a proper term for it, we call it the rest mass. The rest mass. Okay, make sure you know this term, the rest mass. Which means mass at rest. You're not moving. Okay? So mass at rest is m naught. And the relativistic mass, relativistic, is m. You know, it gets heavier and heavier. So, and this m is equal to gamma m naught. Remember, gamma is larger than 0. Excuse me. And so if it's larger than 0, excuse me, larger than 1, that is. So it we, for example, I'll give you an example. You recall, if you are going at the speed of point AC, remember, we found gamma to be 1.67, right? So what would be my mass? If my mass is 80 kilogram, so what's my relativistic mass? Well, it's just gamma m naught. So 1.67 times 80, right? And so I have here 1.67 times 80, answer 135.6. So I'm going to gain mass, lots of mass, 133.6 kilogram. Okay, so I'm going to increase, that's my mass will increase by what? 53.6 kilograms. You see what I'm saying? That's called mass increase, okay? Now, as a result of that, so remember, we have 3 things going on here. You have time slows down as you go faster and faster. Length becomes shorter as you go faster and faster. The mass increases as you go faster and faster, okay? All right. Now, when it comes to momentum, remember momentum is equal to what? mv, right? You know, the regular classical momentum. Well, to be more precise, m naught v, because that's the rest mass, right? So relativistic momentum, without the naught, is basically, well, remember, it is, sorry, I'm just a little bit ahead of myself. It's really mv, but this m is relativistic mass, this one. Got it? So it is mv, but this v, of course, relativistic velocity, you know, some velocity. And this m is really relativistic mass, so this is going to be gamma m naught v. And that's the relativistic momentum. This is what you need to know. Okay, this is called relativistic MTM. Okay? All right. Just accept those formulas until I start, I'll give you some problems. And as I always said, always, before you watch videos, always make sure that you read the entire chapter before, watch the video. The reason for that is because it's really difficult for me to cover everything in the chapter. There's just so much information. If I'm going to cover everything, it's going to be hours and hours of video lectures, which I can't do. So please always read the chapter first. Even if you don't understand something, just read it. Just go through it, read it, watch the PowerPoint. I've heard from some students that they like the PowerPoints. And watch the PowerPoint presentation, the one I provide every week. And then, then you want to watch the video, look at how I solve some of the problems. Then you attempt the problem. Then you do the quiz around the end. Hopefully this will help. I know this is not the ideal situation for you to learn physics, but you know how it is. I wish I was with you guys in class doing problems like we used to do, and all that would have been great, wouldn't it? Okay. Let me just talk about one more thing before I would like to do a couple of problems, at least 2, maybe 3. But one more thing, I want to finish the chapter, finish the concept in this chapter here. So, to recap, so we have the following. We talked about time dilation, Linx contraction, mass increase, and we said that there is also relativistic momentum, which looks like that. Again, we'll see how that works. And then also now the energy. So in classical laws, remember, energy is equal to what? Potential energy plus kinetic energy, right? Remember? Okay. In relativity, the energy is given by this. The total energy is equal to the kinetic energy, okay, plus what is called the rest energy. Okay. Now, what does that mean? First of all, what is rest energy? Now, this is a concept you need to understand once and for all, because we're going to be covering it heavily in nuclear physics chapter, the last chapter of the year. Rest energy. Very important concept. Okay, let's say I have a penny. And the penny, the mass of the penny, the rest mass of the penny, it's about 4 grams. Okay? So if I take the penny and weigh it on a scale, it's going to read 4 grams. Again, whatever we weigh on a scale, we call that rest mass, because it's not moving. It's just sitting there, right? So that's a rest mass. According to relativity, it is possible to take this mass and convert it into energy. Okay? It's possible to take this mass and convert it into energy. This conversion of the energy is called the rest energy. So to convert mass into energy, okay, this energy is called the rest energy. And this rest energy, let's call it E, is equal to m naught times c squared. Okay? So this is rest energy. Maybe I could call it E naught. It's not a big deal. Well, they just call it now for temporarily E naught. I've never seen it E naught, but let's say we call it that. So what is the rest energy? It means if I take this penny of 4 grams and I convert it through energy, it will be a huge, enormous amount of energy, heat, for example. So here, let's see how much energy is that. So it's 4 grams, which is 4 times 10 to the 3 kilogram, right? Times 3 times 10 to the 8 quantity squared. And let's calculate that with my calculator. So I have here 4 negative 3 times 3e8 times 3e8. If I did it correctly, it will be 3.6 times 10 to the 14. So it is 3.6 times 10 to the 14 joule. Okay, that's a huge amount of energy. You know how much energy is this? This is sufficient to power every house in America for a month of electric power. Okay, just to take this one penny to convert it into energy. Isn't that amazing? Okay, so we call that what? The rest energy. And now you know how to calculate it. All you need to do, you take that rest mass, not relativistic mass. Okay? If it's relativistic mass, it becomes relativistic energy. We'll come back to it in a second. But this is the rest energy. Okay? So the rest energy, you take the rest mass, you multiply by c squared, and you will get the rest energy. Got it, this one. Okay? Good. All right. So we said that. Let me go back to that formula that I just showed you right here. This one here. We said that the total energy according to relativity, E, is equal to the rest energy, m naught c squared, plus the kinetic energy, k. Okay? Okay. So what is this E, the total energy? Well, the total energy, this E by itself, okay, I'm talking only about the left-hand side, LHS. E. This E is basically it is mc squared, but such that this m is the relativistic mass, so gamma m naught c squared. I hope this is not too complicated for you. So this one, remember we said m is a gamma m naught? Sorry, not the m squared. I'm a little bit ahead of myself. Here it is. Okay? This means such that, if you're not familiar with the math symbol. Okay? So this becomes gamma m naught c squared. So I can write this formula again, as gamma m naught c squared equals m naught c squared plus k. Let me solve for k. So K is gamma m naught c squared minus m naught c squared, and that's equal to gamma minus 1 quantity m naught c squared. And this is the official expression for the kinetic energy, relativistic kinetic energy. Okay? Make sure you box that. Relativistic kinetic energy. Got it? So now we have studied the following formula. As far as energy is concerned, E equals kinetic plus rest energy, such that kinetic energy is equal to gamma minus 1 m naught c squared. Okay, that's the one right here. And E here is equal to mc squared, where m here is what? Relativistic mass, gamma m naught c squared. Got it? And then, of course, this one is nothing but rest energy, E naught, which is m naught c squared. Got it so far? Okay. Let me show you an example. Show you all that stuff. How does it work? I want to do example 27.7, but this one is a little bit, hold on. I'm looking for something simpler. I don't like to start with a tough problem. Sorry, just give me a sec. I'm looking at my notes here. Let me do number 28 in the book. I think it's homework. Oh, it's right here. Okay, it's right there. You see it? Let me magnify this a little bit. Get that thing out of the way. 28 right there. Okay, he says number 28, level 1. Not bad, I hope. It says right here. Okay, guys? It says a particle is moving with a speed 0.8. Calculate the ratio of its kinetic energy to its rest energy. All right. That's not bad. Okay. Let's see how we do that. Let me move this to the other side. Right here. 28. Okay. So it says number 28. He says, again, let me just look at it quickly. He said, calculate the ratio of its kinetic energy to its rest energy. All right. So we know that the kinetic energy K over the rest energy, which is m naught c squared. You remember what K is? It's gamma minus 1 m naught c squared over m naught c squared. You agree with me on that? Here, let's go back. Here is the kinetic energy right there. You see it? And the rest energy is right there, m naught c squared. So we just basically just do that. And then what will happen even before I do the calculation of this, so basically it's gamma minus 1. That's simple. You see what I'm saying? You just plug it in. And he said it's going at the speed of what? 0.8. So we know that gamma is equal to 1.67, if you remember, right? We calculated that already. So 1.67 minus 1, and that's equal to 0.67. That's the ratio right there. Simple problem, right? I'm looking for something a little bit better than that. Number, well, let me go back to that example. I can't find one. Let's go back to example 27. Example 27. I need to go back to the book. You know what? I'll just read it for you. I have it in my notes. There's no need to go to the book. When I find it. Number 7. There we go. Okay. It says, you know what? I think I have to. I don't have the statement in my notes. Sorry about that. Oops. Go back. There we go. Sorry for that, for the delay here. There we go. Okay, it says, let's read it together. It says, in this example, we will apply the concept of rest energy, blah, blah, blah. Okay, here, specifically, find the rest energy of an electron. Okay, we have an electron. The mass of the electron is 9.09 times 10 to the negative 31. The charge of the electron is that. He said in joules and electron volt. Okay, that's cool. That's an easy part. Second part, find the speed of the electron that has been accelerated by an electric field from rest through a potential difference 20 kilovolt and through 5 megavolt and so on. Okay. All right. This sounds hard, but it's not bad. Okay. Let's see how we do that. Example 27.7. Okay, so the first part, he's talking about an electron of mass, rest mass, 9.09 times 10 to the negative 31 kilogram, correct? This is what he says, yeah? And the charge, basically the fundamental charge, so it's just going to be E equals 1.602 times 10 to the negative 19 coulomb, correct? Okay. There we go. He said find the energy for the rest energy. Well, that's not bad, is it? The rest energy, which is E naught, equals m naught c squared. Well, this is m naught right there, right? So all you need is just plug it in. So that's going to be 9.09 times 10 to the 909 negative 31. Did I get the right answer? Right number? Yeah. Okay. Multiply this by 3 times 10 to the 8 quantity squared. When you do that, you will end up with, I have it in my notes here, you'll end up with 8.187 times 10 to the negative 14 joule. Okay? This is the rest energy of the electron. In other words, if I would take one electron, convert it into heat, okay? This is the heat that you're going to produce. Got it? Okay. Now, he said, what is it in electron volt? Now, this is important for you guys, and especially in the medical profession, that you know the unit of electron volt. It's used a lot in nuclear physics, atomic physics, in medicine, and so on. Electron volt is just a unit, just another unit that measures energy. You know, just like you studied in biology, calories, right? Well, there is another unit that you need to add to your list, and that is the electron volt. It's a simple one. 1 electron volt, 1 eV, is equal to 1.602 times 10 to the negative 19 joule. And where did I get this number? Look at that. It's the fundamental charge. Look at that number. It's exactly the same as this number. Okay? So 1 electron volt is 1.602 times 10 to the negative 19 joule. Okay? So if I have this many joule here, well, how many electron volts? Simple. All you need to do is you multiply that by that, right? Here, or you can put them as a ratio. So I have here, put under the joule, puts in this number, 8.187 times 10 to the negative 14 joule equals what here, right? Call it, say, X. So cross multiply. So therefore, the energy in this case, in joule, is going to be what? 8.187. I'm sorry, did I do it? Yeah, I think I did it right. Times 10 to the negative 14 divided by 1.602 times 10 to the negative 19. We divide those together. Remember, this is in joule and this is in joule. The joules cancel out. You end up with just the electron volt, and that's, in this case, we would get the rest energy is equal to 5.11 times 10 to the 5th electron volt. Okay, now I can convert it another popular unit, which is electron volt, but you can convert it into mega electron volt. Mega means 10 to the 6, so you divide this by 10 to the 6, it becomes 0.511 mega electron volt. Got that? And this is a famous number for the energy of the rest energy of the electron, 0.511 mega electron volt. Got it, guys? Okay. Now we come to part B. He says in part B, he said, find the speed of the electron, velocity, that has been accelerated by a potential field through, from rest through a potential difference 20 kilovolt. Excuse me, yeah, 20 kilovolt. And then later with 5 megavolt. Well, let's just do that, 20 kilovolt. Okay, so what you want to do here, when you're asked to find that, well, first of all, let me write down the total energy. Total energy, as you know, is kinetic plus rest energy. You agree with me on that? Okay. The kinetic energy here is basically, this kinetic energy is what is given to us. This is the only thing that is not obvious. Okay? So this, nothing, the potential difference, really what he meant by that is the kinetic energy. So the kinetic energy here, well, we know that kinetic energy is electron volt. So he says kinetic energy, remember, it is equal to Q delta V for energy in general. Well, he gives us the energy, the voltage. The voltage is 20 kilovolt. And this Q here for the electron, which makes it a fundamental charge. So this is delta V. So that's E is 1.602 times 10 to the negative 19. The fundamental times 20 kilovolt, so times 10 to the third volt. And that's how you get the energy, okay? The kinetic, that's kind of the hardest part, is that you don't see that, but that's how you get it. Once you do that, you'll end up with, if I would calculate that, and that would be equal to, let me use my calculator. So I have here 20,000 times 1.602 negative 19, and if I do it correctly, so the energy here is equal to 3.2 times 10 to the negative 15 joule. Okay, there we go. Now, I want to know the speed. Okay, so now I have this one. And do I know m naught c squared for the electron? Absolutely, it's right here. I just found it right there in joule. Okay, so I know that. And what about the total energy? Okay, what is the total energy? Well, remember, the total energy is what? If you go back to the notes above, total energy, E, is gamma m naught c squared, right? The kinetic energy, I have just found it. It's right here. So 3.2 times 10 to the negative 15 joule. And, of course, m naught c squared is equal to, we already got that, which is right here. M naught c squared, right there, right? Let me change it to a different color. I don't want to confuse with all that clutter. There it is, right here. Right, this is m naught c squared. So all I need to do is so m naught, oops, I didn't read it. It's equal to 8.187 times 10 to the negative 14 joule. Okay? So let's plug in all of that into here. And watch what will happen. So E is equal to that, gamma m naught c squared, equals K, let me just call it K for now. Okay, I already know what K is right here, plus m naught c squared. What I want to do, I want to solve for gamma. Why do I want to solve for gamma? Remember, gamma is what? 1 over square root of 1 minus v squared over c squared, right? Well, here is the v. He said find the velocity. Well, it is. It's embedded into gamma. So if I know gamma, I can find v. Do you see what I'm saying? That's the hard part about this problem. All right. So I'm going to solve for gamma. So the way I do that, I divide both sides by m naught c squared. So gamma is equal to k over m naught c squared plus 1, correct? Now plug in my numbers. K, I already got it, it's right here. So that's 3.2 times 10 to the negative 15 over m naught c squared is equal to, I already written it there, right here, sorry. So that will be 8.187 times 10 to the negative 14, sorry, plus 1, okay? And then we calculate that. Go ahead and calculate with me, see if we get the right same answer, hopefully. So that's going to be 3.2 e negative 15 divided by 8.187 e negative 14. And then we're going to add a 1 to it, rather, and that will be equal to 1.039. So that will be 1.039. That's the gamma factor, okay? Cool. I got the gamma, but gamma is equal to 1 over 1 minus v squared over c squared, right? Well, let me solve for that, okay? One way to do it, you square both sides, get rid of that root, and then 1 minus v squared over c squared, cross multiply, equals 1 over gamma squared, and therefore v squared over c squared, and that's going to be equal to 1 minus 1 over gamma squared. Now you plug in your numbers, okay? You know how to do that. I don't think I want to do it for you. You plug in your numbers, and then you'll end up with v equal to 0.27 c. That's the speed of the electron. Got it? He got 0.27 c as well, right there. I don't know how he did it, but I find my way. Hopefully you understand it. If you don't understand it, please let me know. Okay, I want to do one more problem, and then I'll let you go. We are already over an hour, but I'm going to do one more example, number 27.8, the next example. And then, please, if you have a question about any of the homework problems, post them either under Ask the Professor or under the discussion forum, okay? Just post them and I will supply a solution. I can simply, I can simply, solve it, and I will just take a picture of it and just paste it there, okay? So you can see the solution. I will do it for you, okay? Okay, let's do example number 27.8. It says, now let's apply the conservation of energy. Okay, you have two protons, each with rest mass 1.67 times 10 to the negative 27 kilogram. That's the rest mass. Have equal speeds in opposite directions. So they're going to collide head-on with each other. They collide head-on, then come to a rest. The collision produces a pi meson. Okay, that's just another particle. With a mass, rest mass that is, 2.4 times 10 to the negative 28, okay, which is also at rest. Great. Find the initial speed of each proton and the initial kinetic energy of each expressed as a fraction of the rest energy. All right? Okay, this is how we do it. Let me show you the story first. Let me change it to black color again. Okay, so what you have in here, you get two protons. Here's one, here's another one. They are shot head-on in a head-on collision. Okay, and so this is the m naught. I'm going to call it m naught for the proton, rest mass. Okay, and then after the collision, you have three particles at rest like that. He actually have this picture. I'm copying it from his picture. It's right here. You see it right there? Right there. You see it, guys? So you have two protons in head-on, and then they are collided, and then a newborn particle is born, is right there in between them. It's called a pi meson, okay? And this is typical stuff in nuclear physics collision theory. Anyway, and then he's asking, what is the original speed of the proton before collision? Now remember, all these three particles after collision are at rest, okay? All right. So here's the pi meson. Here's the proton. Maybe I should call that proton. Okay. He gives me that the mass of the proton, the rest mass, 1.67 times 10 to the negative 27 kilogram, and the mass of the pi meson is equal to, let me see, 2.428, negative 28. So we have 2.4 times 10 to the negative 28 kilogram. Okay, there we go. Okay, so what do we do here? Well, let's look at it from terms of a energy before collision. BC, before collision, okay? So what's happening before collision? Well, we have two protons moving toward, I'm sorry, excuse me, toward each other. So each of them has a total energy. Remember, the total energy is equal to what? Here, let me put it on the side. Is equal to m naught c squared plus the kinetic energy, right? This total as well, just by itself, this E is equal to gamma m naught c squared. Remember, this is the total. So the total energy here, I have two of them. I have two protons before collision. So here I have gamma m naught c squared for the first proton plus gamma m naught c squared for the second proton. Make sense? Everybody agree with that? Okay. Another way of putting it, okay? This is one way to do it. Another way, maybe I'm looking for an easier way to do it, is that, remember, each particle has a rest mass plus kinetic, right? Well, we have two protons, so we have two rest masses, 2 m naught c squared for each proton, plus 2 kinetic energies for the proton. Make sense? I'm using the right side of the equation rather than the left side. Okay, we can use this left side. We can use the right side for now. Okay. Now, all right. Now, after collision, what do we have in here after collision? Well, after collision, nothing is moving. So, in other words, if I'm going to use the right side of the equation, there's no kinetic energy anymore. It's all rest energy. Rest energy of what? Well, I have the rest energy of the two protons, so that's 2 m naught c squared, is that right? Plus the rest energy of the pi meson. Okay? Now, conservation law says that the, let me eliminate that. I don't want to confuse you. Again, it's not wrong. I like this one better, just like the way it looks, this one here. So now, because of the conservation of energy, this energy, the total energy before collision, must equal to the total energy after collision. So I'm going to equate those two together. So in this case, I'm going to have 2 m naught c squared plus 2 m naught c squared plus 2 kp equal to 2 m naught c squared plus m pi meson c squared. Is that okay? And so what will happen here, I can eliminate those two together. Is that okay? And then I want to solve for kp. Remember, he's asking for what? He's asking for the velocity, isn't he? He's asking for, I forgot what he's asking for. What is he asking for? He said, find the initial speed. Sorry, he wants the velocity of it. Yes. Okay. So I can now solve for kp, which is, so those are gone. So the kinetic energy of the proton is 1/2 mass of the pion c squared. But what is an expression for kp? Well, hold on. Let me before I go ahead of myself, let me calculate this value. I can calculate, right? So 1/2 mass of the pi meson is given to me, and it's equal to right there, right? 2.4 negative 28. So let me plug it in. So I have 2.4 times 10 to the negative 28 times c squared, which is 3 times 10 to the 8 quantity squared. And when I calculate that, I will end up with 1.08 times 10 to the negative 11 joule. This is the kinetic energy. I'm not interested in it, but this is the kinetic energy. Now, with this, he's asking me for the velocity. Well, I know that, okay? But the kinetic energy in general is gamma minus 1 m naught c squared. Is that right? For the proton, that is. Well, and how do I get the velocity? Well, I get it from gamma, just like the previous problem, remember? Right? So I can take this, equate it with this, make them equal, and then I'll solve for gamma. You see the plan? So let me equate them together. So in this case, I'm going to have gamma minus 1, m naught c squared, which I already got that. But anyway, here it is, equals 1.08 times 10 to the negative 11. And remember, I'm solving for gamma, so let's have gamma minus 1 is equal to 1.08 times 10 to the negative 11 divided by m naught c squared. And so the gamma is equal to 1.08 times 10 to the negative 11 over m naught c squared plus 1. Is that okay? Plug in all these numbers in there. And I'm going to get, again, this is what? What's m naught c squared? It's just the rest mass of the proton. So that's 1.08 times 10 to the negative 11. The mass of the proton, 1.67 times 10 to the negative 27. Multiply this by c squared 3 times 10 to the 8, correct? Squared. All of that plus 1. Do this calculation now. You work it out, and then you'll end up with 0.072 plus 1. And that's basically gamma factor is 1.072. That's what I got. Okay? Now, I'm not done yet. However, we can just say, I'll just go straight down here. But gamma is equal to 1 over square root of 1 minus v squared over c squared. And that's equal to 1.072, right? And so just solve for v squared, which we've done already. You know how to do that. And once you do it, I got v equals 0.36c. Okay? How did you get? It's not clear what he got, unless he didn't finish it. Oh, they're right here. 0.36 right there. Okay. Anyway, then you can do the same problem for the second part, if there is. I'm sorry, there's no second part here. I thought there is a part. Anyway, there we go. And then we can get the velocity. Okay. I'm going to stop right here. I think basically covered pretty much all of the topics that I want to cover for the relativity chapter. Please work on the problems and let me know if you have any questions. Okay? Bye-bye.